Hello everyone, welcome back to my YouTube channel. This is a 2.5 kilowatts inverter using to transformers, which I introduced in a previous video. If you haven't seen it yet, you can find the link in the description of this video. Today, I'd like to share with you this circuit, an H-bridge that uses high-power MOSFET to convert high-voltage DC into pure sine wave AC 220 volts at 50 Hz, just like the standard household power supply. When multiple MOSFET are connected in parallel, the output power can reach from 2.5 to 3 kilowatts. The circuit is very compact. It fits right in the palm of your hand. The high voltage is generated by two transformers and then fed into the H-bridge circuit. I use a voltage sampling circuit with two resistors as a voltage divider, which reduces the voltage by a factor of 10, making it easier to measure using an oscilloscope. The circuit is powered by a 13 volts input. Let's connect a multimeter to the output so we can check the output voltage. When I switch on the controller, the power indicator on the high voltage section lights up, signaling that high voltage is present. Then, when I turn on the H-bridge, the output voltage gradually increases. The measured output is around 175 volts in sine waveform at 50 Hz. The circuit includes a built-in potentiometer to adjust the output voltage. I adjust it to reach 220 volts with a light bulb as the load. The system runs stably. After turning the switch off and then on again, the output voltage ramps up gradually and remains at the preset level. When I disconnect the high voltage section, the H-bridge circuit immediately stops working and its indicator LED flashes to signal a fault. To restart, we need to power off the entire system and then turn it back on. As you can see, the circuit resumes stable operation as expected with a pure sine wave output at 50 Hz. If you enjoyed this video, I'll show you the detailed step-by-step build process in an upcoming video after the introduction to my partner JLC PCB, who provides high-quality PCBs for my projects. JLC PCB provides easy, affordable, and reliable PCB and PCBA solutions, empowering electronics engineers to develop projects efficiently. With 19 years of PCB manufacturing expertise since 2006, running 5 cutting-edge, in-house factories and serving over 5.48 million engineers in 180 countries and regions. Order PCBs from JLC PCB effortlessly. Upload your Gerber file to get instant quote and order in minutes. It's as easy as online shopping. PCB customization, component sourcing, stencil manufacturing, and high-precision assembly all in one place. Get 1 to 8 layer PCBs for just $2, efficient large-scale production reducing costs and bringing you unbeatable prices. Quality and lead time is reliable. All in-house production, ensuring quality stability and strict quality control in every process. Rapid turnaround, lightning-fast PCB production in just 24 hours. Don't miss JLC PCB 6-layer PCB special. Get $30 off with a coupon and enjoy top-quality 6-layer PCBs for just $5. Plus, to unique finish and no engineering fees for via InPad. This is the schematic diagram of the circuit. It uses an EGSOO to controller to drive the H-bridge with 4 MOSFET IRF for 6.0. Here is the power supply stage, which steps down from 12 volts to 5 volts to power the controller. This section is feedback signals to control the output voltage, and here is the PCB layout of the circuit. You can download it from the link I've included in the video description. So, this is what I received 1 week after uploading the Gerber files to JLC PCB. Let's open it up and take a look at the boards. As always, the packaging is very secure and the boards are well protected. Here we can see the PCB quality is excellent, the silk screen is clear, the solder pads are clean, and the alignment is perfect. I also selected the green solder mask, which gives it a professional look. If you take a closer look at the traces and vias, everything looks exactly as designed. This is an important component in the circuit, a ferrite ring core with the dimensions shown in the video. This inductor plays a key role in the circuit. It helps smooth out the current and reduce high-frequency noise, which is especially important in inverter circuits. By stabilizing the current flow, it protects the components and ensures a clean, reliable sine wave output. Without a properly sized inductor, the circuit may produce voltage spikes or distortions in the output waveform. I used magnet wire with a diameter of 0.8 mm to 1 mm and wound 140 turns around the core. The resulting inductance is approximately 3.5 millihenries. Now let's move on to assembling the components onto the PCB. I start by placing the low-profile components first, such as resistors, diodes, and small capacitors. This makes the soldering process easier and keeps everything in place. After that, I move on to larger components like the MOSFETs, electrolytic capacitors, and the EGSOO to controller module. Make sure to double-check the orientation of components like diodes, ICs, and polarized capacitors before soldering. Once everything is in place, I solder all the connections carefully to avoid any cold joints or bridges. This is the circuit after full assembly. Before inserting the EGSOO to control board, we need to power up the circuit and check a few key voltage levels on the board. This step is very important. It helps ensure that the control board will not be damaged when plugged in. I recommend checking the 5 volts regulator output and confirming there are no short circuits or unexpected voltages on the power lines. First, I connect the power supply to the circuit and switch it on. Then, using a multimeter, I check the input voltage. In this case, it should be around 12 to 13 volts. Next, I measure the output of the 5 volts regulator, which powers the EGSOO to control board. The voltage here should be exactly 5.0 volts. If everything is within range, it's safe to install the control module. After I insert the EGSOO to control board into the socket and power on the circuit, you'll see that the LED on the board lights up, indicating that the module is receiving power. After a few seconds, the LED will start blinking, showing a fault condition. This is completely normal at this stage because the circuit doesn't have high voltage input or AC output connected yet. Now I'm checking the gate signals of the MOSFETs on both the high side and low side of the H-bridge. For the low side MOSFETs, the gate signal is a simple square wave switching at 50 Hz. But for the high-side MOSFETs, we see a high-frequency SPWM waveform. This is the sinusoidal pulse width modulation, already modulated to follow a 50 Hz sine pattern. These signals work together to drive the H-bridge properly, allowing the inverter to generate a clean sine wave after filtering. Alright, that's everything I wanted to share with you today. I hope this video helped you understand more about how the inverter circuit works, especially the gate signals on both the high and low sides of the H-bridge. If you enjoyed the video or found it useful, please give it a thumbs up, leave a comment, and don't forget to subscribe to the channel. Your support really means a lot and keeps me motivated to make more cool DIY electronics videos. Thanks so much for watching. I'll see you in the next one.